Matrices have those little brackets with little pieces at the end. The determinant has two vertical line segments, and inside we put the matrix. In this case, let's put 1, 2, 3, 4. This symbolically means the determinant of the matrix 1, 2, 3, 4. It's a square matrix. And the way we get the determinant of a 2 by 2 matrix is really quite simple. We take the first row, first column, and the second row, second column, and I'll draw an arrow, and we multiply them. 1 times 4 is 4. And then we take the remaining number over here, the first row, second column, and the second row, first column, multiply them and subtract that from the first answer. Since 2 times 3 is 6, minus 6, and that gives us a negative 2. So the determinant of this matrix is a negative 2. Okay? Now we're going to take a look at the determinant of a 3 by 3 matrix, and this is a bit more complicated. I'm going to show you the easiest way to do this. There are other ways, and in case your class does not include determinants, or you touch it very lightly as I am here, that's okay. You'll spend more time on this in more advanced classes. But I wanted to introduce this because it is a very good way to solve systems of equations, as we're going to see in the next lesson. But let's go to the next visual. And here we have a 3 by 3 determinant. The first row is 1, 2, 3. The second row is 2, 5, 1. The third row is 0, 3, 2. It's a 3 by 3, a square matrix, which we can take the determinant of. Notice what we've done below. We've repeated the first and second columns. The first column of 1, 2, 0, the second column of 2, 5, 3 are repeated. So we actually have those 5 columns and 3 rows. And then notice the arrows. The arrows going down the diagonal from top left to lower right. And we multiply along those diagonals. 1 times 5 times 2 is 10. And the next diagonal from upper left to lower right is 2 times 1 times 0, which is 0. And then we have 3 times 2 times 3, which is 18. And notice those numbers are added in parentheses as highlighted on the bottom line in this visual. Then, using red arrowed lines, red diagonals, if you will, as opposed to the blue that we used first, we go back from upper right to lower left, starting in the extreme upper right. And we get 2 times 2 times 2, which is 8, plus 1 times 1 times 3, which is 3, plus 3 times 5 times 0, which is 0. And we add those together. And in the next visual, we see the results. We take the sum of 10 plus 0 plus 18, which is 28, the sum of 8 plus 3 plus 0, which is 11, and we subtract. And we can see in this visual that the determinant for this particular matrix is equal to 17. What does that mean that it's 17? Well, right now it has no meaning. It is simply a numerical value associated with that matrix. We will use determinants, as I said, later on. In fact, we'll go ahead and use some determinants right now to find another aspect, another characteristic of a matrix. But I also want you to remember that we're talking about determinants. Earlier on, we talked about a quadratic equation. We talked about the discriminant. Two totally different things. Don't get them confused. The determinant is this number that represents a square matrix. What we're going to do next is look at the inverse of a matrix. Now, what is the inverse? Well, in multiplication, the inverse is the reciprocal, isn't it? Right? We take a number and we flip it over. For example, the inverse of 5 is 1/5. 5 times 1/5 is 1. That's exactly what we're going to do with some matrices. Let's go ahead and go to the board and take a look at the inverse matrix. And again, the kind of matrix we'll take the inverse of is going to be a square matrix. And I'm going to go ahead and take the inverse of a 2 by 2 matrix. The inverse of 1, 2, 3, 4. That's the matrix. And we want to take the inverse of that. And of course, -1 power is what's used to indicate inverse. We talked about F inverse in a much earlier lesson, and we used F -1 to indicate the inverse function. This is the inverse matrix. And the way we do that is the first thing we do is we take 1 over the determinant of that matrix. And I selected this matrix because we already have the determinant of that matrix. And then we take the original matrix and do some changing. Excuse me, the first thing we do is we take the terms in the first row, first column, and the second row, second column, and swap them. The 4 goes here, the 1 goes there. And then we take the terms in the first row, second column, and second row, first column, and change the signs. So the 2 becomes a -2, the 3 becomes a -3. Okay? We know that this determinant is -2. We did that earlier, right, when we got 4 minus 6. So let's replace the determinant with its value, which is -2. And now all we simply have really is -1/2 times this matrix. And of course we saw that multiplying by what's called a scalar, we simply multiply each and every item, each and every element in the matrix by the -1/2. And what do we get? We get a 2 by 2 matrix. Let's see. -1/2 times 4 is -2. -1/2 times -2 is a +1. -1/2 times -3 is +3/2. And -1/2 times 1 is -1/2. So that the inverse of this matrix, 1, 2, 3, 4, is this matrix here. -2, 1, 3/2, and -1/2. Let's sort of generalize that. Let's look at the next visual, which shows us the generalization of the inverse matrix. We have the 2 by 2 matrix A, B, C, D. We want to get its inverse. And its inverse is 1 over the determinant of A, B, C, D times this matrix where we take the items that are in the first row, first column, and the second row, second column, and swap them. So the A goes where the D was, and the D goes where the A was. And the remaining 2 items, we change the sign. So B becomes -B, C becomes -C. And of course, we then, as we did at the board, we figure out what the determinant is, multiply, and we get a matrix. What's the meaning of this inverse matrix? Well, let's take a look at the next visual. And here we have a multiplication problem. The first matrix is our friend 1, 2, 3, 4. The second matrix, -2, 1, 3/2, -1/2, is the inverse of the first matrix. Now, what did we say happens when you take a number and multiply it by its inverse? You get 1. And look at what the answer is. If you don't believe it, go ahead and multiply the rows times the columns. We get this new matrix, a 2 by 2 square matrix, 1, 0, 0, 1. This indeed is what's called an identity matrix. Let's see why. Let's go ahead and take 1, 0, 0, 1, go to the easel and multiply it by something. Let's see. 1, 0, 0, 1. And let's multiply it by, let's say 2, 4, -1, 0, just for the fun of it. First row times first column. 1 times 2, 0 times -1 is 2. First row, second column. 1 times 4, right? 0 times 0 is 4. Second row, first column. 0 times 2 is 0. 1 times -1 is -1. Second row times second column. 0 times 4 plus 1 times 0 is 0. Notice that these two matrices are identical. When you multiply by the identity matrix, it's the same thing as multiplying a number by 1. You wind up with the same answer. This is very important. And this is why the inverse matrix is very important, because we'll use the inverse matrix to divide. Remember the old thing about dividing by a number is the same as multiplying by its reciprocal or multiplying by its inverse? We will do that. And the next and last visual shows us two types of identity matrices. The first one is the one we just looked at, a 2 by 2 identity matrix, 1, 0, 0, 1. The second is a 3 by 3. Identity matrices are square matrices. And notice the pattern. Along that first row, first column, second row, second column, third row, third column, what's sometimes called the main diagonal, we have ones. And all the other numbers, all the other elements are zeros. This is an identity matrix. Can you visualize what a 5 by 5 identity matrix would look like? Well, obviously you would have 1 with 4 zeros in the first row, a 0, a 1, and 3 more zeros in the second row, 2 zeros, a 1, 2 more zeros in the third row, and so on and so forth in a 5 by 5 matrix. Okay. What we have seen in this lesson is we've introduced the notion of matrices, what they are. We can add them. We can subtract them. We can multiply a matrix by a number. We can multiply a matrix by a matrix. We also have seen something called the determinant, which is a number associated with a square matrix. And we've used the determinant to find the inverse matrix. And we saw that we multiply a matrix by its inverse, we get this matrix that acts like a 1 when you multiply it. That is the identity matrix. We will use matrices and determinants in the next lesson, which is lesson 27, to solve the systems of many linear equations. And I think you'll find that using matrices and determinants will make solving those systems a lot easier than doing it by hand. I bet you can't wait.